a lot of in the book talking about contradiction. If a space astronaut travel speed of light, and in that cases, what's the time over there? What's the time on the Earth? That is kind of a certain contradiction or puzzles for you to answer that. So this is the section 9.4. Okay, now besides the time, then come back. Then the next thing we talk about is the length. In which cases, one of the stick is moving in one reference frame. But this meter stick moving, the length of it is contraction from another reference system to look at. So this is LP in moving with the velocity v. This one is on the reference system is not moving. So by this way, L is equal to V times delta TP, in which cases in relationship with this situation. Okay, in this situation. So in that cases, the delta TP equal to 1 over gamma delta T. Then if you plug it in, that is equal to L equal to V times delta T divided by gamma. Okay. Then if you keep doing 1 over gamma, V times delta T equal LP. So 1 over gamma LP, and so this is the form. So L is equal to 1 minus V squared divided by C squared square root LP. LP is right here. But from another point of view, this system looking at the meter stick, it is shortened, they're decreasing, because 1 minus anything is less than 1, so that L is shorter than LP. This is called length contraction related to the speed of light. So then, a lot of people debating in this situation. One of the things is debating is how does this apply to our system? And the gentleman is called Lawrence. He tried to develop this relationship, especially the relationship with the velocity. This relationship about related with velocity is called Lorentz transform equation. So we start this again, this reference plane again. This is one inertial system, this is a second inertial system. And then just as usual, this reference plane moving, and then this V times T, and the distance from here to here is the X, and here is the X prime. So the things we like to say, how to do the transformation. So the X prime in the relativity system equal gamma times X minus VT, and Y pi equal Y, Z pi equal Z, T prime equal to gamma times 1 minus V divided by C squared X. And then he go on and do the other things, the reverse things related. The inverse of this. This equation express gamma and X in terms to represent X prime. This one using gamma X prime represent X. Just the inverse of that. So now we consider the velocity. How do we calculate the velocity in different reference systems? So we do the X prime, Ux prime. What is the velocity in this frame? That equal to dx prime dt prime. dt prime. So from the Lorentz equation, dx prime, you just d this one, dx prime, your gamma dx and then V, I think there's a dt there. Okay, dt. Okay, the dt prime is gamma dt minus v over c squared dx. So yeah, this is a two relationship around d divided. Okay, so if you do this, then this one must have a t here. So in these cases, then ux prime, you go dx prime, dt prime, go through all this math, then you got ux prime equal to ux minus v divided by 1 minus uxv divided by c squared. With this development, you consider as a Lorentz relationship. Primarily is related with the speed in different reference plane. Okay, we take a break, and then the next section is kind of important. It is talking about 9.6. And this is very important, right? On the chapter 9, we have 7 examples, and then plus 2 derivations. One of the important derivation is divide the relativistic energy. Okay. Another one is using this E equal mc squared divided by square root 1 minus u squared divided by c squared to prove that E squared equal p squared c squared plus mc squared squared. So